In this video, we're going to review the basics of complex numbers and in particular pay attention to working with the imaginary part of the complex numbers for some of the video. This is a review of what we already know, but we need to be comfortable with this information to move into using trigonometry to express complex numbers. So first of all, let's start off with what is a complex number. A complex number is a number that can be written in the form a plus bi, where a is the real part of the complex number, and the bi, that's the imaginary part of the complex number. And a and b must be real numbers. So we could have, for example, 3 plus 7i, or the square root of 15 minus 2i. Those are complex numbers, but so is 7. 7 is a complex number because 7 is the same as 7 plus 0i, and 0 is a real number. So even though 7 is a real number, it is also a complex number, because real numbers are part of the complex number system. And 3i is an imaginary number, but it is also 0 plus 3i, and so it's an imaginary number, but it's also a complex number, because imaginary numbers are part of the complex number system. Okay, so when we talk about a complex number, it includes real numbers, it includes imaginary numbers, and it includes combinations of them where a and b are both not 0. That would be one that has a real part and an imaginary part. Okay, so when we start to talk about these numbers, we need to make sure that we understand what is I. So I is defined as the square root of -1. Back in algebra, probably algebra 2, we realize that sometimes we have to take the square root of a negative number. That helps us to solve for the roots of polynomials, and sometimes we end up with the square root of a negative. And so we define the square root of -1 to be I. Now, it's not just useful for understanding the roots of polynomials. I comes into play in system controls and electronics and electrical engineering a lot as well. Now, what does this mean? If I is the square root of -1, so we can rewrite things like the square root of -16. And the way that we do that is anytime we have a square root under the radical, we take that out separate. So we say that that's the same as the square root of -1 times the square root of 16. And the square root of -1, that's I, and the square root of 16 is 4. And so the square root of -16 is 4i. So anytime you have a radical with a negative under it, you need to take the -1 part out separately. So, for example, we'll do another one. What if we said the square root of -8 times the square root of -2? We know that we can multiply the numbers that are under the radical, but when it's a negative, you must take the negative out first. So we're going to rewrite this as the square root of -1 times the square root of 8. And this is going to be the square root of -1 times the square root of 2. The square root of -1 is I. Square root of 8 times square root of -1 is I times the square root of 2. And so what we have now is these two i's can get combined. So we have I squared, and square root of 8 times square root of 2. Since there's no negatives, we can say that's the square root of 16. And so we have 4 times I squared. But now we need to talk about what is I squared. Okay, so if we know that I is equal to the square root of -1, then I squared is equal to the square root of -1 times the square root of -1, which is the square root of -1 squared. And we know that when I square a square root, it makes that go away. The square of the square root just brings the inside out of the radical, and so we have I squared is equal to negative 1. And so 4I squared is 4 times negative 1, because I squared is negative 1. And so the answer here is negative 4. Now, if you didn't take your negative 1 out of your radicals here, if you didn't separate these out to the square root of negative 1, square root of negative 1, let's look and see what this could have been if we did it incorrectly. We could have said, oh, well, maybe we can just do the square root of negative 8 times negative 2, and that's the square root of 16. Oh, well, the square root of 16 is 4, and we might have got just a positive 4. But positive 4 is incorrect in this problem. And the reason is that we're losing the fact that to start the problem, there is a negative under the radical. We need to deal with that first. We need to do it this way first. Now some might argue, well, this is plus or minus, and so then you have to pick, but how are you going to pick which one? You have to go back and make sure you get those square root of negative ones out first. So don't try to do it this way. Simplify them out with your eyes first. Okay, let's talk a little bit more about powers of I. And again, this should be review. So if we know that I is equal to the square root of 1, and I squared is equal to the square root of negative 1 squared, which makes negative 1, well, now we can build up all future powers of I. So let's do I cubed. Well, I cubed is going to equal I squared times I to the 1. That's I cubed. And I squared is negative 1. And so I cubed is equal to negative 1 times I is negative I. So I'm just going to write them over here just to keep track. Okay, I to the 4th is equal to I squared times I squared. And I squared is negative 1. And I squared is negative 1. So negative 1 times negative 1 is positive 1. And now every future power of I is going to be written in terms of I to the 1, I to the 2, I to the 3, or I to the 4. We're going to simplify them in terms of these results. So for example, if I said I to the 5th, I'm going to call that I to the 4th times I to the 1. But I to the 4th is 1. And so I to the 5th is just 1 I. I to the 6th is equal to I to the 4th times I squared, but I to the 4th is 1. So that becomes 1 times I squared, but we know that I squared is negative 1, so that becomes 1 times negative 1. So I to the 6th is equal to negative 1. And so you see that I'm repeating my same 4. If we did I to the 7th, I to the 7th is I to the 4th times I cubed, and I to the 4th is 1, and I cubed is negative I, and so I to the 7th is negative I, just like I to the 3 is negative I. And I think that you can figure out that I to the 8th is equal to 1, because I to the 8th is equal to I to the 4th times I to the 4th, which is 1 times 1. So how do we do higher powers of I? So for example, what if I said I to the 27th? Well, think about it in terms of I to the 4th. Since I to the 4th is 1, we want to get as many of those out as possible. So this is I to the 4th to the 6th, right? Because 6 times 4 is 27, as 24, and then I cubed. So it's really this remainder that matters. So what you're going to do is you're going to take the power of I, and you're going to divide it by 4, and you're going to get a whole number. That's the number of I to the 4ths that you get. And then you're going to get a remainder, right? So it's 6 and 3/4 remaining, right? And this is your power of I that's left there, right? So when you take your 27, you're going to take I to the 4th and figure out how many of those go in. So that's going to be the whole number you get when you divide your power of I by 4. And the remainder that you get is the I that's left over, because 6 times 4 is 24 plus 3 is 27. Now, I to the fourth is 1. So 1 raised to any number is still 1, and then times whatever we have left, I cubed. So this becomes 1 times I cubed, but remember, I cubed is negative I, so this becomes 1 times negative I, which is negative I. So you can do that for any number. Like, for example, we could do it I to the 201. Well, let's divide. 201 divided by 4, that equals 50 with a remainder of 1. Okay, so this is going to be I to the fourth raised to the 50th, because that's I to the 200, times I to the 1, because that was my remainder. I to the fourth is 1, so 1 raised to the 50th times I to the 1 is just 1 times I is I. So I to the 201 is just I. Okay, so that's a little bit of manipulating with powers of I. And then the last thing that I wanted to do is just to review basic functions of adding, subtracting, multiplying, and dividing of complex numbers in this form. And again, this is still review from your algebra skills. And after we've done this review, we'll go into the trigonometric form, the polar form of complex numbers. So let's do a couple of examples. Adding and subtracting complex numbers. So we're going to say, for example, we'll do 2 plus 3i plus 7 minus 6i. We're going to add these two complex numbers. You're going to add the real parts, so you're going to get 2 plus 7. And then you're going to add the imaginary parts, so you're going to get 3i plus negative 6i. And so that's going to be 9 minus 3i. Okay, let's do an example of subtracting. So when we subtract, it's just like subtracting in an algebra problem where you distribute your negative. So if we said 7 plus 15i minus 13 minus 5i, we're going to do 7 minus 13, subtract the real parts, 7 minus 13, and then plus 15i minus a minus 5i. Okay, so you do your real, you put a plus in between, and then you subtract your imaginary. So you subtract the real parts, 7 minus 13, and then you subtract your imaginaries, 15 minus a minus 5, and you have a plus in between them. So we have minus 6, and then 15i minus a minus 5i is going to be plus 20i. Okay, now when we do multiplication, we need to use our FOIL techniques. So if we were to do 2 plus 5i times 3 plus 4i, we're going to either think about it as a distribute both of the first into the second, or you can do it with the shortcut that we use in algebra, is foiling is the shortcut for that. So we do 2 times 3, that's our first, and I'll write it out. First terms, outside terms, 2 times 4i, inside terms, 3 times 5i, last terms, plus 5i times 4i. And then you simplify. So we have 6 plus 8i plus 15i plus 20i squared. We combine like terms, so we have, these are both I to the 1. So we have 6 plus 23i, and then we replace our I squared. This is equal to negative 1, and so we have 20 times negative 1. So we have 6 plus 23i minus 20, and we combine our real parts, so we have minus 14 plus 23i, and that is the product of these two complex numbers. And then the last part of the video is division, and division is really understanding multiplying by complex conjugate. So when we talk about complex conjugates, just a reminder of what this word means. A complex conjugate is a complex number where you change the sign on the imaginary part. So for example, if I had 2 plus 3i, its complex conjugate would be change the plus to a minus, 2 minus 3i. If I had negative 7 plus 2i, I change the sign in the middle, negative 7 minus 2i. These are complex conjugates. If I have 3 minus 5i, the complex conjugate, change the sign in the middle, 3 plus 5i. You're changing the sign of the imaginary part. So when I say change the sign in the middle, it happens to be between the real and the imaginary. But you're changing the sign of the imaginary part. So let's think about the complex conjugate of 6i. The complex conjugate of 6i is negative 6i. Okay, so technically you're just changing the sign. Now, in this case, this is not really an important conjugate. We don't really actually need to do this. The conjugates are most important up here. Because the goal of a complex conjugate is to be able to multiply your original number by a complex number that will eliminate the imaginary part of the number. We want to multiply it by something that creates an entirely real number. So a complex conjugate is a number, a complex number, that when you multiply it by the original complex number, the product gives you a completely real number. So when I multiply 6i and negative 6i, I would get negative 36i squared. And since I squared is negative 1, I would get negative 36 times negative 1, which is 36. But it's not as important here because truly all I needed to do is multiply this by I, and I would have got 6i squared. And that product is a real number. Now, it's not the same. These are different numbers, and the product's a different number, but it's a way in algebra and pre-calculus and calculus, it's a way to move yourself out of the complex system. And so I'm going to do a division problem with the complex number. So let's say that we had 3 plus 2i, and we wanted to divide that by 5i. When you're doing division problems with complex numbers, if your complex number, your imaginary part, so I'm going to say a complex number with an imaginary part, is in the denominator, then the division is going to feel more like multiplication, because what you're going to do is you're going to multiply by a fraction that's equal to 1 that eliminates the imaginary parts from the denominator. And so in this case, I have 5i on the bottom. If I multiply the bottom of this fraction by I, just I, that makes the bottom 5i squared. And since I squared is negative 1, I would have 5i squared, and that's 5 times negative 1, and that's negative 5 on the bottom. So I'm accomplishing my division by getting rid of the I on the bottom. Now, if this was a complex number that had a real part, I would have to multiply it by the conjugate. Now, I don't want to change this. I'm trying to do this division, and so I'm just trying to make the fraction look different but not change it. And so if I don't want to change the fraction, I want to express this as a different way to express this number, this division problem, then I want to multiply it by a fraction that equals 1. So whatever I need to put on the bottom in order to get the bottom to be a real number, I need to put that same on the numerator of my fraction. And so now I'm going to multiply 3 plus 2i times I, and I'm going to get 3i plus 2i squared. But we know I squared is negative 1, so this becomes 3i minus 2, and so this becomes minus 2 plus 3i. And now that division gets me a real number in the denominator, and I could rewrite it. Negative 2 plus 3i over 5 could also be written as negative 2/5 real part plus 3/5 I, imaginary part. And so I can write it as one complex number with a real part and an imaginary part. So that division problem can be simplified out to one new complex number. Okay, and so notice it's not 2/5 I. Just because the 5i is under the 2i, notice that it's not the same there. Okay, so let's do one where it's a little bit more complicated for your conjugate. So let's do this problem. We have 5 plus 2i divided by 1 minus 3i. So we want to do that division. And the way that we do the division is we multiply by a fraction that gets rid of the imaginary part on the bottom. So I'm going to multiply this by 1 plus 3i because that's the complex conjugate, and you'll see that it gets rid of the imaginary part in the denominator. And if I multiply the denominator by that, I want to multiply the numerator because I don't want to change this number. This is some number when I do that division. So if I have a number here, I want to keep the number the same, and I do that by multiplying by a fraction that equals 1. Numerator and denominator are the same, so this fraction equals 1. So we're going to FOIL the top. So we have 5 plus 2i times 1 plus 3i. So we have 5 times 1 plus 5 times 3i plus 1 times 2i. That's the insides. And then the last, plus 2i plus 3 times 3i. And then in the denominator, we're going to FOIL the denominator. So we have 1 times 1 is 1. And then 1 times plus 3i. And then minus 3i times 1. So we have minus, well, I'll just write it, times 1 times minus 3i. That's a minus there. And then we have minus 9i squared. And so this is what the complex conjugate's doing. I have plus 3i and minus 3i, so those cancel. And now on the bottom, when I replace that I squared with negative 1, I have only real numbers. So let's simplify the bottom of that first, the denominator. We have 1 times 1 is 1. These two canceled, and we have minus 9 times I squared is minus 1. So I'm going to continue with the bottom here. I have 1 minus a minus 9. So I have 10 on the denominator. Now in the numerator, we're going to simplify the numerator. So we have 5 plus 15i, 5 times 3i, plus 2i, 1 times 2i, plus 6i squared. Okay, and we have 15i plus 2i, well that's 17i. And I'm going to do this in one step. I squared, that's negative 1, right? So 5 plus 6 times negative 1, that becomes 5 minus 6, so that becomes negative 1 plus 17i in the numerator. And so now I know that this division, 5 plus 2i divided by 1 minus 3i, is equal to negative 1 over 10 plus 17 over 10i. And that's how we do division with complex numbers. So there's a worksheet, there's an assignment to just practice. And again, this should all be a review from Algebra 2 and also from the beginning of our year. We did a little bit of this at the beginning of our year.